The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Thank you for joining us today. My name is Emily Kuda, and I'm Percona Senior Manager of Marketing Programs. We're going to get started in just a moment. I just want to conduct a little bit of light housekeeping for those of you that have joined us. Can you raise your hand using the hand icon to let me know that you can hear me? Great. Okay. So next during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible. Those that aren't addressed will be answered in a follow-up blog entry on Percona's database performance blog. In addition, a recording of this webinar and the slides will be made available to everyone within 48 hours or less. So with that said, I'd like to thank you for joining today's webinar as we talk about running MongoDB in production. This is the last part of this series, part 3, presented by Percona's Senior Technical Architect, Tim Valancourt. Take it away, Tim.
Hi again, everyone. Hopefully you've been following along, but if not, the slides were available for the other parts. And as we go through, if there are any terms that sound unfamiliar, maybe just go back to part 1 and 2, and this part might make a bit more sense if you've missed. Work at Percona on MongoDB. So we'll have a little bit of time for questions, but we'll go quick.
Sorry about that, Tim. We lost the whole first part of that. All right, so the first slide, that was Tim introducing himself, him giving a bunch of a background and everything that that he does. A little bit about the agenda today. We're going to be talking about troubleshooting, schema, data integrity, scaling, and read and writes. That's our high-level agenda for today's discussion. And Tim, I don't know if you can hear me at all, but if you want to, we'll wait a couple of minutes to see if you can get your sound to come back. All right, I apologize for that, folks. If you're just joining us now, looks like we're having a little bit of technical difficulties with the audio right now for Tim's audio. If we can't get him to get his audio back up, what we'll do is we'll do a recording again, and then we'll try it. Tim, can you hear us?
Yes, I can. I've connected with a different connection.
Okay, there we go. We can hear you again.
Okay, I apologize for that, everyone. I'm actually using a second connection which might be a good thing to include with production stuff, is always having a backup plan. This is a bit of a slower connection, so you might hear a little bit of garbling, but let's try. Okay, so troubleshooting. The usual suspects that you'll run into with troubleshooting performance problems will usually be one of 3 categories: locking, limits, and resources. And I usually look at kind of a triangle of those 3 categories. When I look at a performance problem, it's rare that you'll have a performance problem that hits all three of those categories. Usually a problem that you're going to run into, like maybe a deadlock or a lock in the database, is probably not going to be due to max connections or something under resources. It's probably more of a logical thing. And on the flip side, it's unlikely that a lock would cause your CPU or network to use more resources. So generally, because there's a lot of areas to take in troubleshooting, I usually try and go with one of these three. And if it's not, no signs of locking, I'll move on to maybe limits or resources being hit. So that's just a methodology. Moving on, when you need to troubleshoot a problem in production, and that can happen quite often, I would look first at monitoring, which we talked about in a different part. But if you don't have monitoring set up for MongoDB, you could easily run a db.currentop on your server that will show you quite a bit of what's going on right now on the server. So you'll see things like query IDs, the original query that was sent by the client, its locking details and things like this. So that's great to see when you first hop onto a server what's going on, if there's a problem right now. You can filter this output with filter documents. So you can use $onops to say that I only want to see operations that I've created as my user. That's useful if you need to use that. So this is just an example of that output of db.currentop, and it's actually an array of operations happening in the server. So just going through the tools that you can use to troubleshoot, db.stats is another one that will show you the size and estimated number of documents and average sizes in the collection. That's useful if you want to know just how much storage this uses or how much data is being could be possibly queried by a collection scan. The log file is another source of troubleshooting data. We talked about in the security section of an earlier piece that this should be a log that is not readable by everyone because it has a lot of details, usually the real query. You're going to get a bit more details from this than other places that you'll be able to see queries that happen over 100 milliseconds that the server samples, and also a lot of errors and permission denied kind of problems with the server. Anything the server is doing or can't do will mostly show up in that log file. Here we're looking at a slow query. I've broken the log down so that pieces of it are bold and on their own lines, but actually this line we're looking at was just one huge blob in the log file. So we can see this operation was a find and modify, and it examined one key, so one index key, one document. It matched one document, modified one document, and that's it. So this is a fairly efficient query because we can see that it just scanned an index. Keys examined means that an index was scanned. Only one row in the index was scanned. One document was fetched after, and the find query only matched one document. So that's a pretty efficient query we can see from this log file, just as an example. The operation profiler is a great feature of Mongo where it writes performance data to its own server into another collection. And Percona's monitoring tools rely heavily on that collection to tell it how the database is performing. So hopefully the last few tools, if you use PMM, Percona Monitoring and Management, you don't need to look at most of what we've just talked about and maybe over the next few slides because a lot of this is automated, like the current op commands and such that we showed earlier. Some of that data could be more easily grabbed from a web browser with PMM, but you could definitely grab it from these pieces, and the profiler is one of them that both PMM and manually you could query. This profiler is enabled in the log file, and you can set the threshold of milliseconds of when it would actually consider something slow, much like MySQL slow log. The difference with the profiler is it's set to a maximum size, so just like the AuditLog, if too much is written to it, it will expire. It'll delete the oldest entries and add more with a capped collection. Useful metrics that you'll find in the profiler are the query itself that was the cause of the profiler, logging this, the number of keys examined again, the documents examined, write conflicts, yields, and locks. And all of those things I don't have time to explain exactly, but the key ones here are keys examined and docs examined, and the ratio between how many index keys were examined and documents. So if you see in kind of any output a query that only scans documents and scans no indexes, that's probably going to be a bit of a slower query, and you could speed it up by adding an index. The explain cursor function that there's an example of on the right here, you can add this to the end of any fine query. Will show you what the query planner is actually doing to execute the query, much like other databases again. And you'll see not only the winning plan, but also the plans that were rejected, what indexes, and kind of why the optimizer thought this was the best index or the best way to perform the query. Combining the profiler data and explain together is very nice, and this is, again, something PMM automates for you in the web browser to a certain extent. But on the left and right here, I have the output of a explain plan and a profiler document for the exact same slow query. So you can see if I combine those two outputs or just look at them manually, I can see quite a bit of what happened. The explain is going to show what the executor wanted to do before the query, and the profiler documents showing what happened after. So kind of the before and after of this query, if you're using those two things properly. Percona server for MongoDB, PSMDB, has a free open source feature called the AuditLog that was intended to duplicate the MongoDB Enterprise feature, auditing feature of MongoDB Enterprise that you need to pay for support and contracts to get with MongoDB Inc. We have this as a free and open source feature, and it logs to a BSON file on disk. Basically all the operations you would typically want to know about with maybe PCI deployments or tight security deployments that need to kind of see everything that's gone on in the server. So this logs out to an on-disk BSON file that can be read with MongoDump. On the next page, I just have this MongoDump -- pretty as the command line flag will actually print it in a way that's easier to read. And that file can be ingested back into MongoDB or into another system for analysis. That's another directory to make sure that's not world readable. Just like your log file, you don't want every user on a Linux system, let's say your Nagios plugin or some monitoring user on your system shouldn't be able to read stuff like that. Only a DBA should be able to read the AuditLog or security a team, but definitely not any user, especially in environments with LDAP where any person in the company can log onto a server. Because that's a great way to expose some data. The cluster metadata is another place to look. This is a bit rare, but if you have clustering problems, there's a set of collections in the config servers that you can look at to answer a few questions, like which databases are sharded, The chunks collection is very interesting. That shows all the pieces of the data and where in the cluster those are. So I can't go into all the details of these collections, but you can run find queries on them and look at exactly what your MongoS and MongoD processes are looking at when they are a cluster. So you can answer a lot of questions about the cluster that way. So a lot of the tools I just talked about are automated, hopefully. The intent is in PMM's query analytics feature. This has an agent on your MongoDB servers that uses the profiler that we discussed just now to feed data into our monitoring system that will actually explain some of the reasons why your queries are slow, or at least that's the intent. It's very useful because it's a web browser. In our security talk, we discussed limiting how many people can access a server, so that if your job is just not related to needing access to a database that you just physically can't get there, and that's not for any reason other than just having fewer people to ask when a problem happens on the server, it's better to have 10 people to ask what happened on the server at 8 p.m. versus 10,000. So that's the only intent there. PMM QAN allows you to display this data that typically you'd need to hop on a server to see in a web browser without leaking data, because we actually normalize the queries in a way that the sensitive data is essentially removed. So in this example here, in query normalization on this page, 1, 2, 3, 4, 5, 6 would actually be displayed as number signs, and you'd understand which query it was, but not necessarily sensitive data in the query. An alternative to using this, which is a web browser system, is the PT MongoDB Query Digest tool, which is a command line tool that does some of what QAN's trying to do, but not quite as much. So if you don't want to set up QAN or PMM to automate that, you could definitely just use the CLI tool to get maybe half of the value, maybe less than that. This is just a screenshot of PMM on our demo system, and some find queries that it's finding on a system that is arranged by latency and ratios of keys examined and documents scanned. So we're trying to show you the most inefficient queries first, basically, or provide that functionality. Other tools you could use are mlogfilter for filtering the log file. Just because I use Mongo a lot, I know what to use in grep or different find and replaces to look at the log file, but it's not always pretty. So the mlogfilter is a nice tool for chopping up the log and removing parts that you're not interested in. And Percona's tools, MongoDB Summary and Query Digest, I just mentioned, are good for just kind of understanding a little bit on the shell about the environment and its slow queries. Schema design and workflow is almost its own talk, so we're just going to go through what I would kind of look at if I was asked to run an app in production that was already written. We won't have time to explain how to write an entire app from scratch, but definitely what to look for when it's going to production. So data types is one of the biggest things that I like to check on MongoDB deployments, and the reason for that is wasted space and performance. So the most common thing that I see in MongoDB deployments is numbers stored as strings. So on the third line here, I have in quotes the number 1, 2, 3, 4, 5, 6, but because it's in quotes, that means it's actually not a number, it's a string. And that has serious impact on how it's stored on disk, and also, probably more importantly today, how it's stored in memory. I know disks are cheap, and you might say, I've got 80% free disk space, it doesn't matter, but it's actually more the memory you want to worry about with data types, because when you put an index on a field that is a string, it's going to take up much more space in your memory, and that's going to impact performance. So This is the most common one I see, is just numbers with strings around, or sorry, double quotes around it. If you see that, that means it's not a number. And just at the bottom here, I have an example JavaScript that would convert a full collection of fields that have numbers as strings to real numbers. And that would save you, in the example of using 8 numbers, an 8-length number, that would save 25% space in memory if it's indexed and also on disk. So that's a pretty serious savings. You do need to make sure that your app is still going to like that, but for the most part, Mongo hides the details of strings and numbers to you. So it's unlikely that your app would have any problems converting a string to a number, but always be careful and test that. The other one is dates. If you see, I hope you can see my mouse, probably can't see my mouse moving, but I'm actually highlighting this date in double quotes. MongoDB has a concept of real date types. So if you stored this date that I have, 2017-08-17, 10 a.m., as a real date, it would take 52.5% of the space, so quite a bit of savings there. That's another thing that I see very commonly in apps, is just a string instead of a data type. Very last is Booleans as strings. So if you have the word true in quotes and false in quotes, you could store that in 47% of the space, yes, 47% of the space if you stored it as a real Boolean, not a string. So very important things to look at, and remember that you're wasting memory more importantly than disk, because disk is cheap and people usually don't worry so much if they're wasting that, but it's memory that you should worry about. And when you scan through the index, that there's more memory for the CPU to iterate through. Indexes, we've mentioned that a few times now. It looks like default behavior got cut off on this slide, but the default index in Mongo is typically a B tree. So we'll just talk about that and probably not text and geo here. Yeah, an index makes a collection lock on any storage engine until it completes, like most databases, unless you use background true, which is a feature of create index that tells it to just do it lazily whenever it has time, is probably the best way I'd summarize it. But there's some downsides to that. If it has an error and fails, you don't actually get an error bubbled up to the shell to say this index has failed. It will just log to the server log file, and maybe you think it was executed and it wasn't. Another problem is you don't exactly know how fast it's going to try and run it or when. So it's not great for production, is how I'll summarize it without wasting too much time. And my suggestion that Percona recommends is rolling out an index one node at a time by removing it from the replica set, restarting it, applying the index while it's not part of the replica set, and then adding it back. That's the way today that we can guarantee that your production won't be impacted by adding an index if that happens after you've already launched and you have users hitting the database. So that's not fun that you have to do it one at a time. You could automate it, but think of the user experience here, that the user doesn't even really know this happened. And I've worked on a lot of databases where they really, really would know that you added an index. So I think that's amazing. It puts a little more work on the DBA to have to remove the nodes one at a time, add them back. But it's a great user experience. They don't even know it happened. And that's kind of the intention of a lot of architecture decisions in MongoDB, is to not impact the application. I would try and avoid drivers that auto-create indexes, because indexes need some manual work to really know, is this a good idea? You can always add indexes, but they'll hurt insert performance and sometimes read performance if the optimizer has too many plans that could answer the same query. You can also waste a lot of disk space, and maybe something that's not thought about too much is if you use logical backups, you're going to add a lot of time to your restore time if you add more indexes, because they have to be rebuilt on restore. So lots of things to think about there. And that's why I don't think a driver should be making those decisions for you. It's a lot better to have a DBA set those, set up a call, talk to the developers, and execute that index in a way that doesn't impact production. Very important, I should have put this maybe first, this last point here, that indexes have a direction in Mongo. So if you're sorting ascending, make sure your index is ascending on that column so that it's most optimized for that sort. And then also put indexes on fields that are sorted last in your index. I just want to make sure I didn't skip over a point there about, okay. Compound indexes, so when I said put your sort field last, that would be in a compound index where you have many fields compounded together as a single index. So in the case of a sort, your last field should be your sort field, and again, match it to the direction that you're going to sort, ascending or descending, so that it doesn't have to be really suboptimal for the server to execute. And then composite keys are read left to right. So if you only use a piece of the composite, so in this example, on the first example of a composite key I have here, username, status, date, and count. If I do a query only on username, Mongo is still able to use that index and only chop the first quarter of it off. So what that means is I have 4 bullet points here with 4 indexes. They're actually all duplicates of the first one. If you look, they all have the same fields, username, status, date, account. The second one has 1 less, and so on. All of the indexes, number 2, 3, and 4 there are duplicates, and you can delete those because the optimizer would be able to chop the first index to whichever piece it needs. So that's a common mistake I've seen where, for example, you have an index username status and an index username, and of course you don't need the second one. To look at your indexes, you use get indexes on the collection, and that will give you an output showing all of them. My hope is we can write a tool in the future for Percona to make that easier to see duplicates, but no promises yet. But that's definitely something we're thinking about right now. I mentioned efficiency ratios earlier, and when I say that, and when PMM says that in our monitoring, it is the ratio of index to disk, basically, being hit for a query. So are we hitting the index, or are we scanning for documents? So for example, if a query scanned 10 documents to return 1, its efficiency would be 10%, or better not to use percentages because it could exceed 100%. Its efficiency would be 0.1. And of course, ideally, the ratio would be 1-to-1. That's 1 document, one index scan. So to finish off, schema workflow, unfortunately, it's a big topic, but I'm just going to try and finish it off here. Antipatterns. So the first one I see a lot is find queries that don't specify what it wants. So by default, a find will return an entire document, and maybe you just want 1 field from it, enabled true or false, for example. But maybe you have a document that's 10 megabytes, and you're doing a find, and maybe it's easy for the server to execute it with indexes, and it's in RAM, and it's in the cache, but it's sent over the wire. If you're using Python or whatever driver, it has to marshal that off to different structures, and 10 megs, that's a lot of stuff. So definitely specify what you want when you have a find query. And if you don't need the entire document, you just need a piece of it, you can specify, like any database, MySQL would be select asterisk is kind of what Mongo is doing by default. You should always specify what you want there. Sorry, I just skipped ahead. Also using $where does a global lock because it uses JavaScript. So that's just something you might not be aware of until something hits production, but that causes locking because the JavaScript engine in Mongo still does quite a bit of locking. That should be another anti-pattern actually, is just using the JavaScript engine. If you can use the aggregation framework instead, I'd try and do that because it runs as compiled C code much quicker. Another is many ands and or conditions. So any database isn't good at this, or I shouldn't say any database, a graph database is optimized for this. But MongoDB and most relational databases are not. And what I mean is doing a query and saying where product ID equals a list of 200 product IDs. The database can do it, but it just doesn't really know a great way of doing it. It's just not going to be the fastest thing. Don't have time in this talk to exactly talk about how to fix that, but my point would probably be that if you need to do a very large amount of ands and ors, do that in many queries. Limit it to maybe 10 at a time, 50 at a time, 100 at a time, and join that result somewhere else because it's not great for the database to do. It could be cheaper to do to not hurt your expensive database resources that way. But like anything, if you ask it to do something inefficient, Mongo will do it. So it depends. It depends what the goal is. I've copied the same quote from the last slide here. So data integrity does not apply to this quote, but we'll move on. So this section is just about making sure the data that's going into your server doesn't get lost after. We've already talked about backups, so it doesn't quite apply to that, but more how journaling happens. So on this slide, we're just going to talk about how really the journal protects you. Most database storage engines in Mongo sync to disk every minute. So if you're not using a journal, that's potentially how much data you could lose on a crash if there was enough replication delay and enough bad things happened. So it's just like any other journal in Postgres or MySQL that it's a write-ahead log of your changes that are reapplied on crash recovery. So that's important to know. It's by default enabled a journal, so I'm going to skip ahead because it would be, you'd have to explicitly disable your journal to need to know more about what we have on that slide. So of course, the replication in Mongo is asynchronous. It's not like Cassandra, for example, or Galera or Percona extra DB cluster, where when you do a write, it goes to every node and we wait until every node has it. It doesn't quite work that way, but the very neat thing about Mongo is it can pretend that it works that way. So MongoDB is using asynchronous replication for the best performance, but from a software logical perspective, it can pretend that it has the same consistency that I just mentioned. And pretend's probably the wrong word, but what I mean is write concern is a feature added to Mongo that when you do a write, you can say this many nodes need to acknowledge it. Just like what I mentioned with Galera, ExtraDB, and Cassandra, the difference is behind the scenes, the replication is asynchronous, and really you're just waiting for each of those nodes to say, I've reached the same point on the op log. But to the driver and to the application and to crash recovery and integrity, that doesn't matter. It's exactly the same thing. So the great features that you can do per write, for every operation, you can say, this is how many nodes need to acknowledge it. You can also say majority as just the string majority, which will take half of your nodes plus rounded up to 1 to make sure that basically if there's a failover, that document is going to exist. So what I mean there is if you have a 3-node replica set and you write with replica set or write concern majority, at least 2 nodes will get that change before your application is returned saying it's written. Okay, done. So what that means is if there was a failover, MongoDB's replication is smart enough to pick only one of the 2 nodes that got that change because they're the most up to date. So making this slide very short and wrapping it up, you can use write concerns to basically make replication pseudo-synchronous. It's not actually going to be synchronous, but your application is waiting until that change is written to everyone. So best of both worlds, I feel. What else can I say here? In 3.4, the majority journal was changed. So with your write concern, you can say if it needs to be journaled to disk as well. So that's another layer in your write concern is, do I write to 3 nodes or do I write to 3 nodes to disk? So that's kind of what the jtrue journal flag would enable in Mongo, is if you set jtrue in your write concern, everyone's going to write it to disk. This journal default changed in 3.4, so if you don't specify jfalse, it's always going to write to disk. So some users at Percona have upgraded to 3.4 and seen worse performance because they were relying on the default to be false when it changed to true. So look out for that and test for that, but if you see worse performance going from 3.2 to 3.4, look to see if you were specifying your journal flag. It's probably just the default that changed. Okay, so replica sets can roll back, and unlike most databases, this is a very different concept than a rollback in Postgres or MySQL or Oracle. When you hear the term rollback in Mongo, that means that there was replication lag and a primary crash. So let me explain that. So because there's asynchronous replication in Mongo, if a master is ahead of its secondaries or replicas, those replicas can become primary, but they might not have every single change that the crash primary had. So in this example, let's just go through the example on the slide here. Primary writes 10 documents, but the secondaries have only replicated 5 and 7 of those changes. So we're going to lose 3 of them basically. Because we've lost the primary, MongoDB is going to elect the node that had 7 of the 10 changes. That becomes primary. And then when we fix the server that broke, whatever happened doesn't matter. We bring it back up, and it has the documents, the 3 documents that the secondary that took over didn't. Remember, we wrote 10 documents. So the secondary that took over only has 7. The primary that we brought up has those extra 3. The problem is when that old primary comes up, it's going to become secondary and throw away those 3 documents because it needs to join the replica set again, and the primary of that replica set doesn't have those documents. That's hard to explain, but hopefully that makes sense. What happens is that node is going to write the 3 extraneous documents out to disk into a BSON file called in a directory called Rollback. So this can be a surprise to some, and this can be avoided by using write concerns, because using a write concern of greater than 1 means that we know that that document is on multiple nodes. If you're using the default behavior with no write concern, this is the risk that can happen, is those 3 documents can be rolled back and the replication continues without them. So what's the end result here? That sounds very doom and gloom. Monitor for the existence of a rollback directory, and probably email your DBAs or your developers and ask, what should we do with those 3 documents? Do we add them back into the system, insert them, or just forget about it? The key is use write concerns to avoid this, or if you don't use write concerns, expect this to happen. And maybe that's okay. MongoDB is giving you all the tools to make those decisions basically, but not assuming which you want to do. it's going to err on the side of performance. On the opposite side, and very similar to Cassandra again, not similar to extra DB cluster, I feel, is read concern, which allows your reads to also acknowledge multiple members. So what that means is if you read with read concern majority, you're only going to read what a majority of the members can agree on. So if the majority of your members are behind in replication, you're actually going to see a pretty old copy of the data, but one you know everyone has. And that's another way of avoiding the risk of rollbacks or failover problems, because if you're reading from the oldest state, not the newest state, the oldest state everyone can agree on, you know after a failover that that state's still going to be true, because the oldest node, as fast as the slowest node is kind of, you know that that's not going to get rolled back because the oldest state is not going to win. So that's another way if you really need to be sure that after a failover, a catastrophic problem, that this read that I just did will be true exactly the same after. Use a higher read concern, and same with the write concern. An example I would use a write concern is if you're adding a user to your system, and later we'll refer to them. Let's pretend we have an ordering system, and I'm adding myself as user Tim, and then I create 10 orders to my address, to Tim's address. Let's pretend a failover happened and my user document Tim was rolled back, but not my orders. That would be pretty confusing because a user who doesn't exist has all these orders. So if you're going to refer to something later in other documents, I really highly recommend you use a write concern to make sure that we know 100% that all the references to that will not be referring to nothing, won't get orphaned. Replication we talked about earlier, I believe is ordered by time. So as we've kind of discussed here, it's asynchronous replication, so it's ordered by time. There can be a delay between the replica executing something, and that's what write concerns can avoid. Definitely monitor the size of your oplog. I don't think we've mentioned that earlier, that your oplog needs to be from start to finish the length and time that you need to bring a new member up without initial sync. So of course, adding a new node to replication will bootstrap it, will send it your full data set, and will add it to the system, but it has a cost that a full sync is very expensive. Let's pretend you have 2 terabytes of data and add a new member. 2 terabytes of data is going to get sent to that new member. That's pretty expensive. I'm removing a detail there that there's compression now in the wire protocol, so you would probably compress some of that data as it's going, but not good. So you definitely want to try and use a backup to add a new system to the replication, and your oplog needs to be as long as the backup is old, basically. Disaster recovery, lots of features Mongo has for this. We talked about one very cheap one that in backups is storing a hidden secondary in another location. Even if you have no disaster recovery plans, why not store a hidden secondary in another location just for backups? So even if your production gets hit by an asteroid, sure, you can't bring it back up on this one hidden secondary node, but you have the data, so that would be nice. If you're going to take a backup anyway, so to me, it doesn't really matter if my backup's coming from Europe or North America, if it's going to be uploaded to S3 or something. So definitely that's a possibility to store a hidden secondary, another location, and because it's hidden, it doesn't matter how slow it is or how behind it is. That's a good one. Also, you can use geo-distributed architecture to use tag-aware sharding. We just put out a blog at Percona's performance blog about that, or it's just about to be put out. And I hope I didn't spoil someone's blog if it's not out yet about tagging and sharding. So that's another way to kind of fence off where data is being read and written to, so that so that it has some kind of geo-redundancy disaster recovery. So scaling reads. Oh, okay. So correct data types we already went over, but that's where I was just confused as we've covered that. But having correct data types are going to help read queries a lot. So, you know, true in strings versus true will actually make a read faster because it's easier to fetch. Predictive workflow. So if you know a user is going to do something the moment they write something, why not cache it on the write? Or think about how you can prepare the database for that versus just letting it hit the database. So what I mean there is if you're using a count query often to count how many documents are in a collection, why not change the app to increment a counter when it inserts something so that the read is very cheap. It just has to read this one computed value instead of doing a count that actually has to scan the collection and actually count it. So I think I actually have another slide that goes over that a bit further, but predict your workflow. And if you know that this query is going to be hit very often, maybe make the query that's not hit so often a bit slower and do a bit more work in that query to benefit the query that does get hit harder. In this case, you would probably add a counter and make your update or insert a bit slower, but during that insert or update, you would increment the counter. And what that means is the find would be dramatically more efficient, and the insert update is a bit slower. Maybe that's okay. Usually that's okay. External caching is another one. So if you have just a really big query that does something crazy and computes a lot of stuff, cache that. You could throw that into a collection and use the TTL feature of Mongo that would expire it out after a certain amount of time where that data isn't true anymore. You could also, you could write it back to Mongo. You could write it to memcache, which is a bit faster, but very primitive. For read scaling, secondary preferred read preference, which read preference tells your driver what nodes it can read from. Secondary preferred read preference is needed for horizontal scaling of reads because otherwise the default is you read from primary and you only have one of those. So scaling reads can be done by just adding more secondaries, but you have to have secondary preferred or secondary read preference to benefit from that, or your driver is just going to read from the primary. So that's a really big point underlined. Read scaling, your driver has to ask for a secondary. You could also use tagging to say this secondary is SSDs and this secondary isn't, and maybe I only want to read from the SSD one. Lots of things you can do with tags that will be on blog soon with Percona. So just kind of mentioned it, you can get linear star. I put an asterisk beside linear scale out of reads. Really, I can't see why it's not linear. I just don't want to be wrong about that. But basically, if you get 1,000 queries per second from a secondary, adding that exact same hardware and another secondary should get basically double the read performance, as long as you're using the right read preference that reads from secondary. So, but yeah, be aware that when you add a new member, I already said it, you could be bootstrapping your entire data set to it. So try and use a backup when you add them instead of letting the replica set send the entire data set from the primary, which is probably a node you don't want to make any slower. And this is a bit duplicated, but basically high read systems, which are most systems I ever run into, love summarized data. So if your system does a lot of reads, make your writes slower. And I don't mean slower, but do more of the work, hide the work in your inserts and updates so that your reads are really cheap. It just takes 1 penny for the server to execute, but you added a little bit of work to the insert to achieve that. And the most scalable apps I've ever worked on, this is a big, or one of the biggest parts that got it there is the developer sitting there and making the trade-off and saying this query can be slower or more expensive at the to help out this query, which really just cannot be slow. So think about that. And almost always you can add more work to your inserts and updates. I just find that's always true. Websites are usually 3/4 read versus 25% write workloads. So I already mentioned it. If you have count queries, move them to counters. Just increment a counter instead of letting the read query be inefficient. And if you have really huge aggregations, yeah, store them in a TTL expiring document in another collection. I call that the poor man's view for Mongo because there aren't views really, but this would achieve it, and the cache would, it kind of acts as a cache that would expire it as well. So you could say, here's this aggregation summary, cache it for 10 minutes, and then it'll get deleted. Another interesting thing you can do to make reads cheaper is use change streams added in 3.6 that lets you watch a collection and lets your code basically watch a collection like a message queue for changes. Some people use the AuditLog like this, but this is much nicer. Go look into it if you're doing that, because you'll probably be amazed how nice it is. And that would be great for writing some code that summarizes something or increments counters or caching, and just make it watch your orders collection, and every time an order comes in, go increment something or do something like that so that the reads could be faster. So that's a cool feature that you could plug into and write some backend code to summarize some of your data. And spreading the workload to other search tiers, caching tiers, it's not a bad thing. I'm not saying Mongo is bad, but it's some things are better suited for other things, like a real search engine like Apache Solr is going to have a few more features and perform a bit better at text searches and complex things. So really, like any database, use the right thing for the right job, and maybe don't try and ask Mongo to do everything. If you want it to be a bit faster, maybe start to move caching off to cache servers, things like that. It can do a lot, but using too much of Mongo can also hurt. We're running a little short on time because of my connection problems, but we'll speed through here. Sharding is too big of a topic to really discuss in depth in this talk, but sharding is how you basically achieve write scalability when you've ran out of capacity for writes. And what we just discussed was reads. If you ran out of read capacity, what would you do there? So in general, think a lot about your shard key. There's great documents out there that will explain it better than I can right now in this talk, but make sure your shard keys don't have monotonic incrementing values forever. So numbers that just go 1, 2, 3, 4, 5, 6, that will be a really bad sharding index. And also text, just because it stores less efficiently, doesn't shard quite as well, and very large fields for the same reason, that it would just use more space. Also avoid shard keys that will cause a hotspot. So I always like to use the example that if you're Twitter or a social media site, you probably don't want a shard key that's going to make all your really big users, celebrities, whoever, politicians, all land on one shard, because that would be really silly. So put a lot of thought into the shard key and think about what happens if 5, 10, 20% of this shard, all of these users become the most famous ones. What now? You can always add more to your composite shard key so that it becomes more granular and can be sharded more evenly across the cluster, but that does have a cost to read performance. So the more you shard, the heavier read performance because of potentially crossing shards. So lots to think about there. I just said a lot of things to worry about, and we don't have too much time to go into it, but make sure that's something you spend a good meeting or a few days on when you're writing a big app that's going to go into production. Are we making the right decision with the shard key? Because you have to re-import the data if you're wrong. Deployment methods for sharding. It's a really daunting thing to deploy sharding. There's a lot of components, but you could start with one shard And really, if you know that you're launching something that will become popular, but right now it's not, or we're just starting right now small, you can start with sharding with one shard. And the great thing about sharding is you can add shards online. You just press a button, add the hardware. Well, don't press a button, you run a command on the MongoOS that will add the shard. And you can do that at low peak by disabling the balancer and doing it at a certain time, or just say, do this whenever you want, balancer, add this shard. Another great thing is if you have an app that you just know is going to be really popular. I worked in gaming, and we knew the moment we flip the switch for this app, 10,000, 100,000 million people are going to hit this thing. Pre-shard your collections. And don't have time to explain exactly how to do that, but chunks get split by the server when they exceed a certain size. If you pre-split your chunks for your entire range of your shard key ahead of your product launch, this saves a lot of work for the balancer, or sorry, for the cluster and the chunk splitting to do, which is an expensive operation. So I can't go into that too much, but if you've thought about your shard key and know that you're going to get a ton of writes, just a huge, the doors are open and people are flooding in situation, pre-shard the collection with the ranges that you know will be used, and that will basically do the work ahead of it. And of course, before launch, your disks are sitting quiet because you don't have users yet. You're just you're waiting for people to show up, so you have the disk performance sitting there ready for you. So if you, let's pretend you have a collection with 1 to 100 possible values. If you pre-shard that 10 times, each chunk would have at 10%. And with that, we've reached the end. I've kind of glossed over some topics there because it is just an hour that we have here, and now just 3 minutes for a few questions. But if we run out of time, we can definitely put together a blog, and I'd like to do some future webinars and blogs on the topics I glossed over. So with that, any questions?
Thanks for that, Tim. Our first question is it possible to connect PMM with the Mongo Atlas?
I wouldn't be able to answer that because I don't work on the PMM team, but I have heard discussions that we were at least trying to come up with a solution, but I can't answer for sure right now. I believe the holdback was SSL support, and yeah, I better let someone from the PMM team answer the rest.
Thanks. Let's see. Our next question is, how do you handle versioning since Mongo users with the read-write privileges can make changes, since the schemaless is one of the attractions to Mongo by devs?
Versioning, okay. I think I understand the question. And one of the features that I would enforce the schema, if you mean from a software perspective, versioning, is using the schema validation that was added in 3.6 that allows you to basically allow Mongo to deny documents if they don't match a certain schema. So that can be done with the create collection command. When you create a collection, you can now in 3.6 specify exactly what needs to be in a document that comes into that collection. And if it doesn't have that, it will be denied. An example could be the document has to have a username, and the username has to be a string, and you'll get an error when that's rolled out, or sorry, when you try and do an insert on that. I've got a blog article about that. If you meant versioning from the server, minor versions of Mongo can be upgraded just 1 secondary at a time, and you can fail over. So major versions are a bit more complicated. But I think you're discussing software versioning, so I would use the schema validation.
Thanks, Tim. Our next question is, are there ever rollbacks that are not caused by latency between nodes?
Rollbacks, yeah. You could just have a node crash because of a power supply issue. I think that's probably, I think we're talking about the same thing here, that a rollback could be caused just by latency and pings, and then an election happens. But yeah, just a regular failure like a disk dying or a data center disappearing or a power supply, a plug being pulled on the power supply, or another one, not just latency. An asteroid hitting the data center, those things.
Oh my. Well, I hope that doesn't happen.
It's more of a joking scenario people talk about, yeah.
An asteroid, great. Well, I think that concludes our, our webinar for today. Thank you so much, everybody, for tuning in today on part 3 of our series. And I'll be sending out an email later today. I'll include both part 1 and part 2 in case you missed that as well. And we hope to see you on future webinars. Thank you for joining us today, and thank you, Tim, for presenting.
Yeah, thanks everyone, and sorry for the connection issues. Always have a backup plan.